Hello maths fans, welcome to the latest video from Tom Rocks Maths and I Love Mathematics, where I'm answering the questions that have been sent in and voted for by you guys at home. This week, the winning question is, how many ping pong balls would it take to raise the Titanic from the ocean floor? Now this may sound a bit silly and a bit like science fiction, but this was a real theory that was put forward in the 1970s as a possible method to literally raise the Titanic from the ocean floor. Believe it or not, the ping pong ball idea is one of the more sensible theories that have been put forward since it sank in 1912. The Titanic, of course, was meant to be unsinkable, sort of famous last words, and on its first voyage from Southampton in the UK, sailing to New York in the US, it unfortunately hit an iceberg and was lost at sea. And in the sort of 105 years since, various theories have been put forward about how to raise the ship from the ocean floor. Some of the wackier ones include injecting the ship with 180,000 tons of Vaseline, which is buoyant, and so the ship would gently float to the surface. Or perhaps injecting it with liquid nitrogen, which is super cold, and so the whole ship would freeze as a giant iceberg, and then again floating back up to the surface. There's something poetic about an iceberg taking it down and then bringing it back. But many of these wouldn't work for several reasons, mainly being cost. It would absolutely cost a fortune to actually go through with any of these plans. And also, we now know that it's actually heavily damaged. The ship split in two when it sank, and the back half has almost completely disintegrated from when it sank and crashed into the ocean floor. And if we tried to move it, it's so fragile that it would basically now just disintegrate. And then that's not to mention the fact that the whole site of the wreckage is actually protected by a UNESCO convention, meaning it can't be touched or changed in any way. To be able to do the calculation and actually answer the question, we're going to have to make a lot of assumptions. And the first one is that the Titanic remains in its original shape. So it's still in one piece. And I've got a lovely drawing of the ship here, roughly what it looked like as far as I can remember. And we know, of course, its size, its dimensions, and we know its weight, which is really important because if we're going to raise something from the bottom of the ocean, we need to know how heavy it is. And the original weight of the Titanic is 47.5 million kilograms. Now, our second major assumption relates to the reason why this theory actually failed in terms of trying to really bring the ship back. And that's that the ping pong balls would be crushed by the pressure at the depth where the Titanic lies. So the resting place of the ship was actually discovered in 1985. It's around 370 miles off the coast of Newfoundland in Canada. And it's at a depth of 3,800 meters. So a very long way down in the Atlantic Ocean. And at this depth, the pressure is immense. So at the surface of the ocean, sort of in the air just around us, the pressure is equal to 1 atmosphere, which is also the same as 14.6 pounds per square inch, or PSI. At the depth of the Titanic, the pressure is over 6,000 PSI, which is quite frankly insane. And a human would definitely be crushed at this depth, and a ping pong ball without a doubt would go a very long way before it got to this depth. Now that we've discussed the assumptions that we need to be able to answer this question, I'm going to tell you about the two mathematical concepts that we need to be able to actually get the answer. And the first of these is Archimedes' Principle. Now, Archimedes is the guy that you're thinking of. This is a man in ancient Greece who was a philosopher, mathematician, scientist, and he did run screaming down the street, "Eureka, I've solved it!" completely nude. And the reason he was doing this was he was taking a bath and he'd actually figured out how to calculate the buoyancy of an object. And he was so excited that he'd figured this out, sort of doing a home experiment in his bathtub on himself, that he just got up and just ran down the street screaming, being just completely so excited about his discovery. So if we have here our ping pong ball or just any spherical object, when it is submerged underwater, there are two forces acting on that object. There is the weight or the force of gravity pulling the object down, so the heavier the object is, the more that weight is pulling it down. And there's the buoyancy force, which is to do with the force sort of pushing the object up, which is why some objects float. So a ping pong ball, for example, will float, and that's because the buoyancy force pushing it up is greater than the weight of the object pulling it down. What Archimedes had figured out, and what Archimedes' principle says, is that the buoyancy force of an object, the force pushing the object upwards, is equal to the weight of the fluid which has been displaced by that object. So in other words, you take your object, you work out the volume of your object, and then you work out how much that volume of the fluid which your object is in would weigh. And this is where our second mathematical concept comes in, and that is how to compute the volume of a sphere. The formula for the volume of a sphere can be very nicely derived using an integral equation where you change coordinate systems into spherical polar coordinates, and then you can do the integral directly. But rather than going through all those steps, I'm just going to quote the formula. And I've written it on the board here. The volume of a sphere of radius r is equal to 4/3 pi r cubed. And so that should be simple enough. We just need to know the radius of a ping pong ball. And fortunately, I've actually got my own ping pong ball. And it says on the ball that the radius, well, it tells me the diameter is 40 millimeters, so 4 centimeters. So the diameter is the distance all the way across, and so the radius, the distance from the center to the edge, will be half the diameter, which in this case is 20 millimeters or 2 centimeters. So plugging that into our formula, we will get the volume of a single ping pong ball. So the volume of one ping pong ball is 33.5 centimeters cubed. Now, that is the amount of water which is displaced by one ping pong ball. And according to Archimedes' principle, we need to convert that into how much 33.5 centimeters cubed of seawater would weigh. Now, for freshwater, we have a very nice relationship where 1 centimeter cubed of water is equal to 1 gram in terms of weight. That's how much 1 centimeter cubed of water weighs. Very nice relationship. But, of course, the Atlantic Ocean is seawater. It's salty. And salt ions weigh more than water molecules. So those salt ions that are in there replacing the odd water molecule to make the water salty actually weigh a little bit more. And across the world, the density of seawater ranges from 1.02 to 1.03 grams per centimeter cubed. And for the Atlantic specifically, the answer is 1.027 grams per centimeter cubed. And so the weight of seawater that is displaced by a single ping pong ball is equal to 34.4 grams. Now, going back to our force diagram, remember that we have to subtract off the weight. So this here, this weight of water is equivalent to the amount of buoyancy, the force pushing our ping pong ball upwards. But of course the ping pong ball has a weight pulling it down, and we have to subtract off the weight of the ball from this value. And again, going back to my ping pong ball, it tells me that it weighs 2.7 grams. So our final answer, in terms of the overall buoyancy force, the sort of total force acting upwards, is just 34.4 minus 2.7. So now we are very nearly there. We know the total weight of the Titanic. It's 47.5 million kilograms. We know the buoyancy force, the total remaining overall buoyancy force of one ping pong ball, to be equivalent to 31.7 grams, which means a single ping pong ball can lift up 31.7 grams. Converting 47.5 million kilograms into grams, we have 4.75 times 10 to the 10 grams divided by 31.7, and that gives you a final answer of 1.498 billion ping pong balls. So, by any stretch, that is a lot of ping pong balls. On average, it costs around 50 cents or so to buy a single ping pong ball. And so, basically needing 1.5 billion of them means it would cost around $750 million to buy all the ping pong balls that were required to lift the Titanic from the ocean floor. And that is probably more money than it would cost just to build a brand new Titanic. Thank you everybody for watching. I hope that I've answered the question, and I also hope you've had fun. Please do subscribe if you like what I'm doing, and also be sure to check out my website, tomrocksmaths.com. You can also find me on Facebook, Twitter, Instagram, all at tomrocksmaths. And I will see you next time with the answer to another question that you guys have sent in and voted for. Thank you.